Today I'm going to explain you the module 4, that is syntax analysis phase. So which is the second phase of compiler design. Now before we get started, let me give you a quick tour on this outline. A role of parser, context-free grammars, top-down parsing, bottom-up parsing and parser generators. We gone through a role of scanner. Now it is the time to study the role of parser. In our compiler model, the parser obtains a string of tokens from the lexical analyzer. Parser verifies that the string of token names can be generated by a grammar. We expect the parser to report any syntax error in very intelligent fashion and also recover from commonly occurring errors to continue processing of the remainder of the program. For well-formed programs, a parser constructs a parse tree and passes it to the rest of the compiler for further processing. Therefore, the parser and the rest of the front end could well be implemented by a single module. Generally, there are two types of parsers for grammar. That is top-down parser and the bottom-up parser. As implied by their name, top-down method build a parse tree from the top to the bottom. That is from root to the leaves. Bottom-up method start from leaves and work their way up to the root. In either case, the input to the parser is scanned from left to right, one symbol at a time. Let us consider the grammar here. So this grammar actually concentrate on expression and the terms. This particular grammar is very challenging because of the associativity and the precedence of the operator. So associativity and precedence are captured in the following grammar, which is similar to what we described in the previous session. That is expression, terms and the factors. E represents expression consisting of terms separated by plus signs. T represents terms consisting of factors separated by star sign, that is multiplication sign. And factor derives either parenthesized expression or identifiers. So let us denote this as a first grammar. Let us consider one more type, that is E derives TE dash, E dash derives plus TE dash or epsilon, T derives FT dash, T dash derives star FT dash or epsilon, F derives bracketized E bar ID. So let us denote the equation 2. The grammar 2. The grammar 2 actually obtained from the grammar 1. Let us see the suitability of these grammars. The expression grammar 1 belongs to a class of LR grammars that are suitable for bottom-up parsing. LR stands for left recursive grammars. This grammar can be adopted to handle additional operators and additional levels of precedence. However, it can't be used for top-down parsing because it is a left recursive. So we're going to explain what is left recursive in the later session. So look at the grammar set in 2. So which is non-left recursive variant of grammar 1, which is used for top-down parsing. See, what is the job of compiler? Actually, we say the compiler converts high-level language to a low-level language, or it is used to convert source program to a target program. It is nothing but the object program. Suppose we have to design a compiler in such a way that it will process only correct programs. If that is the case, its design and implementation is very simple. But Compiler is expected to assist the programmer in locating and tracking down errors and also, if possible, correct the errors. Therefore, here we have to discuss what are the common programming errors that can occur at many different levels. The first error is lexical error. The lexical error includes misspelling of identifiers, keywords, or operators. Example is, let us consider a keyword is for, right? In C language, we have a keyword something like for, while, etc. If the spelling mistake, what is the spelling mistake? One E is extra. So such type of errors are detected in lexical analysis phase. The second is syntactic errors. Okay, syntax error. In general, we say it is a syntax error. So syntax error include misspelled semicolons or extra or missing braces. For example, let us consider we'll write something like main and after that we'll start the braces and we'll write so many instruction, but we forgot to place the last brace. So this is this is detected as a syntax error by the compiler. Semantic error. See, what is the difference between syntactic error and the semantic error? Let us consider this case. See, we have something called the expression here. So what is the expression? It is binary expression. Operand, okay, two operand and one operator. But instead of placing one operator, we place two operator, right? So this is called as semantic error. So we can say semantic error include type mismatch between operators and operands. Let us consider we have another example. Mm, we wrote a function. Okay, the return type of the function is void. Understood? So what is the return type of the function? It is void. And in the function definition, we'll write so many instruction and finally assume we're going to return integer variable. Okay, so what is the return type of the function? Void. What is our function does? It will return something, right? Okay, void means return nothing, but our function do something. So this is called as semantic error. So these errors, okay, so we have something called the error handler in a parser has a goals that are simple to state but challenging to realize. So these goals are report the presence of errors clearly and accurately. Recover from each error quickly to detect subsequent errors. Okay, time is very important. Add minimal overhead to processing of correct programs. How should an error handler report the presence of an error? At the very least, it must report the place in the source program. That is, line number must be specified. Where the error occurs, that line number should be noted to the programmer. Okay, so actually this task is difficult. Error recovery strategies. Once an error is detected, how should the parser recover? Although no strategy has proven itself universally acceptable, a few methods have been broad applicability. So we have the following recovery strategies, that is panic mode, trace level, error production, and global correction. The panic mode recovery. So discard input symbol one at a time until one designated set of synchronization token is found. So what is the synchronizing token here? It is nothing but the delimiter such as semicolon or flower bracket, whose role in the source program is clear and unambiguous. The second is trace level recovery. On discovering an error, a parser may perform local correction on the remaining input. That is, it may replace a prefix of the remaining input or by some string that allows the parser to continue. So trace level replacement has been used in several error repairing compilers as it can correct any input string. A typical local correction is to replace a comma by semicolon or delete an extraneous semicolon or insert a missing semicolon. The next is error production. augment the grammar with the production that generate the erroneous constructs. And global correction says that choose a minimal sequence of changes to obtain a globally least cost correction. Let us consider an example. Given an incorrect input string x and grammar g, these algorithm will find a parse tree for a related string y such that number of insertion, deletion and changes of token required to transform x into y is as small as possible. We have already seen our specific uh, grammar formation, right? So we studied regular grammar. So in the regular grammar must follow rule like left hand side only one non-terminal, single non-terminal on the left hand side, and have a right hand side that is epsilon or a single terminal, or a single terminal followed by a single non-terminal. So this is nothing but the definition for regular grammar. Now, so we have a concept called the context free grammar. So what is context free grammar? So context free grammar have a left hand side that is a single non-terminal and have a right hand side, right? So what is the right hand side? Right hand side means we have something called the combination of terminal and non-terminal. So more formally, we can define what is a grammar, I mean context free grammar G. So G is a quadtuple, that is v comma sigma comma r comma s, where v is the rule alphabet which contains a non-terminal and terminals. Alphabet is subset of v. What is r? R is a finite subset of rules. What is s here? S is the start symbol. So now consider this particular grammar, that is expression derives expression plus term, expression derives expression minus term, expression derives term. What is term? Term derives term star factor, term derives term or factor, term derives factor. What is factor? Factor is nothing but the expression, bracketized expression or identifier. So here, what is non-terminal? Non-terminals are expression, term and the factor. What are the, sorry, that is non-terminals. So terminals are plus, minus, star, slash, bracket, open, bracket, close and identifier. So this is one example for context-free grammar. Now consider the concept of derivations and parse tree. Context-free grammars do more than just describe the set of strings in a language. They provide a way of assigning an internal structure to the string that they derive. This structure is important because it in turn provides the starting point for assigning a meaning to the strings that the grammar can produce. A grammatical structure of a string is captured by a parse tree, which records which rules were applied to which non-terminal during the string derivation. The parser that given a grammar G and a string W decides whether the W, I mean a string that belongs to a language L. If it is, create a parse tree that capture the process by which G could have derived W. So in general, we can say what is a parse tree? Parse tree means it is something called a tree, right? Tree means we have root and leaves. Every leaf node is labeled with an element terminal, also epsilon. The root node is labeled S, that is the start symbol. Every other node is labeled with some elements of capital V, that is non-terminal. Okay, so with this explanation, let us see how to derive, what is the rightmost derivation and what is the leftmost derivation. So this concept we already studied. So let us recall that Let us consider, so the previous grammar, that is expression and term, right? So let us consider the first rule in the grammar. I mean, symbolically we represented by number, okay, 1, 2, 3, etc. E derives E plus E, or E star E, or just a minus E, or bracketized expression, or ID. Okay. Let us consider the derivation minus ID plus ID. So what is the leftmost derivation here? The leftmost derivation, I mean during the derivation process, the leftmost non-terminal in the working string is chosen for expansion. What is rightmost derivation? The rightmost derivation is one in which at each step the rightmost non-terminal is chosen for expansion. Okay, this is the difference. In the leftmost derivation, the leftmost non-terminal is selected first, and in the rightmost non-terminal is selected. Okay, so let us see that in leftmost, so what is the string here? That is id plus id, bracketized id plus id. What is the symbol? Minus. Therefore first I'll choose the first production. What is the start symbol here? E. E derives, because the string is minus, I'm going to choose a rule 3, that is minus E. So which is the leftmost symbol now? Only one, right? What is that? E. The leftmost non-terminal is capital E, that is replaced by bracketized expression E. What is the rule? Rule number 4. Because we have bracketized expression. Now how many non-terminal? Only one non-terminal. So we have to select, that is the leftmost, that is capital E. So what is capital E now? Capital E is replaced as E plus E. That is according to rule 1. So what is E now? Now let us consider. So how many non-terminals we have? Exactly two non-terminal. Let us choose the leftmost non-terminal first. Therefore, the E is replaced with ID. That is rule 5. Now it is minus bracket ID plus capital E bracket close. Now let us select only one, sorry, only one non-terminal is left. That is minus ID plus ID. That is rule 5. Now consider the rightmost derivation. In the rightmost derivation, the same process actually. E derives minus E, E derives bracketized E, E derives E plus E. Now, instead of selecting the leftmost E, we're going to replace rightmost E first. Right? E derives ID. Now after that, ID plus ID. So this is what the difference. Okay, hope you understood what is leftmost derivation and what is rightmost derivation. Now consider the parse tree. How to generate the parse tree for the example minus id star id. See, this is the leftmost derivation. We can choose leftmost or rightmost derivation. That is, I mean, no problem here. So E derives minus E. E derives minus bracketized expression. E derives, here we'll choose minus E, E plus E star E, ID star E, ID star ID. So the parse tree means we have to select the start symbol as a root node. So which is the start symbol here? Capital E. Then E derives minus E, right? Now the non-terminal E in the second level selected as minus, already selected. So bracketized E, right? Bracketized E. What is E now? E is nothing but E star E. So select ID, ID. So this is what the parse tree. So minus ID star ID. Okay. But the concept is it possible to generate a parse tree? Is it possible to generate a unique parse tree from the given grammar? If not possible means if there exists more than one parse tree for a given string, then it is called as ambiguous grammar. What is ambiguous grammar? Listen carefully. A grammar that produces more than one parse tree for some sentence or a string is said to be ambiguous. Or in another way, an ambiguous grammar is one that produces more than one leftmost derivation or more than one rightmost derivation for the same sentence. Got it? Either two parse tree or two leftmost derivation or two rightmost derivation. Let us consider with this example, that is id plus id star id. See, we can construct a parse tree. Look at this. So the first one we'll choose plus, right? E derives E plus E. Then E is replaced with ID, and the rightmost E in the first level is replaced with E star E. Then ID ID. Therefore it is ID plus ID star ID. In another way we can see ID. So we generate the string ID plus ID star ID. In the next parse tree, instead of selecting, see in the left, just go through this parse tree. The left parse tree chooses E derives E plus E first time. The root is replaced with E plus E. But in the second parse tree, E is replaced with E star E. Okay, then the left E is replaced with E plus E and the right E is replaced with ID. Hence, the string will be or sentence will be ID plus ID star ID. So, the string is same, right? How many parse tree? Two parse tree. Hence, this grammar is ambiguous.